Okay, so this is going to be a short lecture. I want to continue where we left off on the discussion of sinusoidal oscillators to talk a little more about the theory and the mathematics of negative and positive feedback. It's a very important topic, and I have found that especially the positive feedback, most textbooks don't discuss it very satisfactorily. So this is a very short discussion, but I hope you will keep this forever in your long-term memory. Okay, so we start with negative feedback. This actually we did most of this last semester, but I'm going to revise it and then quickly add to it. So we start with this simple circuit with the input applied to the positive terminal. We have R2 and R1, and we'll assume the op amp to be ideal except that it has a non-infinite gain. So we write the equations as you may recall, at least some of you. This is how we started the op amp discussion last semester. So we start from the basics. The fundamental equation describing this amplifier is that the output voltage is equal to the gain of the op amp times the difference between the voltages applied at the two inputs. So we say VO is equal to A into VI minus V minus, where V minus is the voltage at the negative input node. Now, if you look at this R2 R1 path, then we see that V minus can be written simply by voltage division in terms of VO. So we say V minus is R1 by R1 plus R2 into VO. Of course, we are assuming that no current goes into the op amp. That is part of the assumption of ideality of the op amp. So we put this V minus back into the first equation. So we'll get VO equal to AVI minus A into all this stuff. And then we take this whole term containing VO on the other side. And then we solve for VO. So we'll get VO equal to AVI, which is this AVI. And this 1 plus A into R1 by R1 plus R2, which comes from here. And we can write this in a standard feedback form as A over 1 plus A beta, where beta therefore is R1 by R1 plus R2. And if A beta is much greater than 1, which is the assumption of a very large op amp gain, then we can ignore this 1 and the A's will cancel, or here A's will cancel, and we'll get 1 plus R2 by R1 into VI, which is what we have seen last semester. So you are familiar with this equation. VO is equal to 1 plus R2 by R1 VI. Remember that the input is applied to the positive terminal of the op amp, therefore the gain is positive. Now qualitatively, let us think about this. Just kind of, this is called a heuristic phenomenological argument. Let's just think about this. So if we say that VI increases by a tiny small amount, then by this equation, the basic equation of the op amp, or as VI increases, this signal goes through the op amp and it causes VO to increase because VI is applied to the positive terminal. As VO increases, because of this feedback path, V minus increases. But as V minus increases, because there is a negative sign here, VO decreases. So this is why this is a negative feedback circuit, because the effect on the output of the original input signal and the signal due to the feedback path are in opposite directions. So VO increases due to a change in VI, but VO decreases due to a change caused by the feedback path. And these two being in opposite directions is what defines negative feedback. Okay, what we'll do now is we want to analyze this circuit for a transient input. So we say, suppose VI is a step, voltage step. We want to see what the output would look like. So this is what we want to do. Now, how do we do this? So let's say Vi is a step, and well, we look at, actually we can't look at this equation because there is no frequency or no capacitors or anything here. So if we look at only this equation, then if Vi is a step, Vo is also a step. But what we want to do is we want to include some frequency dependence or some some frequency dependence in the gain A and see what happens. So here is what we'll analyze. We've not done this before, this kind of analysis in this form. So I'm just going to kind of jump a lot of mathematics here. So this is what we are going to do. When we discussed feedback in the first of the series of these lectures, these online lectures, we had considered a transfer function for the op-amp to be a single pole transfer function, and we said let A be equal to some constant divided by 1 plus j omega by omega 0. So omega 0 is a 3 dB frequency, and this is a single pole transfer function. This we did for an input that was sinusoidal, and this we've seen before in sinusoidal steady state analysis last semester, and a little bit when we did Bode plots this semester. Now, without any justification or explanation, I'm going to say let this j omega be replaced by s. Or in other words, we say that this form of the equation is actually a Fourier transform of the original differential equation, and from a Fourier transform, let us jump to a Laplace transform. So the Laplace is S, and I assume that you know the very basics of Laplace transform to know that S is a complex frequency, and it can be written as sigma plus j omega, where sigma is the real part and j omega is the imaginary part. So Laplace is a generalization of Fourier. So I'm just going to make this transition without any further explanation or mathematical justification. The reason for doing this is that, of course, as we saw in detail last semester, j omega, or in equivalently Fourier transforms, allow us to analyze circuits in sinusoidal steady state, which we had done last semester. Laplace transforms allow sinusoidal steady state analysis because it has a j omega in it, but they also enable analysis for any arbitrary time varying inputs, because the input can be transformed to Laplace domain for any arbitrary time varying input. So that this is, we're going to assume this and analyze this circuit for a step function applied at the input. So we'll say A is equal to A0 by 1 plus S over omega 0. Okay, so let's see the mathematics. So this is the same equation I've written here. So what we do is we substitute this A equal to all this in our A over 1 plus A beta. So this is A over 1 plus A beta. This for j omega we did in the first of this series of lectures also. So we take the 1 plus S over omega naught down, and then we'll get 1 plus S over omega naught plus A0 beta. Then we take 1 plus A0 beta common, and we can write VO as this. So this is A0 over 1 plus A0 beta divided by 1 plus S over all this. And let us write this in the form A0 closed loop. So the numerator we write as A0 closed loop divided by 1 plus S over omega closed loop. This also we saw earlier. Now I'm going to write this slightly differently. I'll just kind of multiply and divide by omega CL. So we write it in this form. Now we say, suppose Vi is a unit step function. So we do the analysis for that specific case. So we say let Vi be a unit step function where with Vs is some constant voltage magnitude. So we say, well, I want to find the Laplace transform of Vi so that I can use it in that previous equation. the Laplace transform of the unit step is 1 over s. I assume you already know this. If you don't, you will study it in mathematics, the mathematics course. So is a Vi of s. The Laplace transform of Vi of t is Vs over s. We substitute that in the equation that we just derived. So you get omega CL is here, s plus omega CL, Vs by s. Now we want to find V as a function of time. So we want to find the inverse Laplace transform of this. Now the way to find the inverse Laplace transform of a function like this is to do partial fractions. So we do partial fractions here. So VO can be written as ACL and VS come out, and the rest of it can be written in this form. You can easily verify that these two are equal. Having written in this form, it is easy to take the inverse Laplace transform, because the inverse Laplace transform of 1 over s is of course simply 1. The inverse Laplace transform of 1 over s plus something is equal to e raised to minus something t. And therefore we get the output as a function of time equal to a constant into 1 minus e raised to minus omega CL into t, which is an exponentially decaying function. In fact, if you recall, a single pole transfer function indicates a single energy storage element in the circuit, and we know very well that a single storage element in a circuit will cause a single exponential when a unit step is applied to the input. So this is a very well-known result. We've seen it multiple times before. So just kind of qualitatively to plot this, initially the output voltage is 0 and it rises exponentially to a final value. I have just taken some value 5 volts here for this plot. Okay, now let us do the same analysis for this circuit here. And how is this circuit different from the previous one? All we've done is we've changed the polarity of these two. So we've applied the input at the negative input terminal of the op-amp, and the output voltage is fed back to the positive input terminal. This is called positive feedback. When the output is connected to the positive input terminal through some feedback network, this is called as positive feedback. Now let us go through the equations of this. Same equations, there will be small differences. So again we say this is still valid, VO equal to A into V plus minus VI, V plus minus VI. V plus can be written as VO into R1 by R1 plus R2. So we write that here. Then that V plus can be substituted here. And then that will have a VO. So we take the VO term on the other side. Now notice that the VO term on the right hand side is positive. So when it goes to the left hand side, it becomes negative. So when we solve this for VO, we will get two negative signs here. Minus AVI divided by 1 minus A R1 by R1 plus R2. And again, this term is just beta. So we could write this as minus AVI over 1 minus A beta. Now again, if we assume fairly and justifiably that the magnitude of A beta is much greater than 1, then we can ignore the 1. Then the negative signs will cancel, the A will cancel, and we'll get apparently VO equal to 1 plus R2 by R1 into VI. In fact, the same result that we got for negative feedback. And interestingly, this is not correct, and we'll see why this is not correct. And this is the part that does not really get discussed in most textbooks. Honestly, I don't know if Cedra and Smith discusses this or not. Okay, qualitatively, if VI increases, because this is a negative sign, VO will decrease. If VO decreases by this voltage division, V plus will decrease. If V plus decreases because of the positive sign, VO will decrease. So any change in the input causes a certain change in the output, and the feedback path causes a change in the output in the same direction. This is positive feedback. If Vi increases, Vo decreases. V plus decreases, Vo decreases. If both the paths cause the output to change in the same direction, we say this is positive feedback. And as we'll very quickly see, when this happens, this relation is not correct. We'll see why. Okay, so what we'll do is now we'll do the transient analysis for this circuit. So we'll assume again that A is equal to A0 over 1 plus S by omega 0. And we substitute this in the A over 1 minus A beta in this case. And then solve this. So we get minus A0 over 1 minus A0 beta, which is the same form as this one here, minus A over 1 minus A beta. In the denominator, we get omega 0 into 1 minus A0 beta. This minus is critical. So what does this do? If A0 beta is in magnitude is much greater than 1, then we can ignore this 1, and then in the denominator we'll get 1 minus S by omega 0 A0 beta, which quantity we call as omega CL. In the numerator we'll keep this as it is and we call this A0 closed loop. This is the difference between positive feedback and negative feedback. Okay, so A0CL of course is equal to approximately 1 by beta, omega C is all this. So we write this and then we apply a unit step or a step function at the input. I should not keep saying unit step. Vi is a step function because it has a magnitude Vs. Okay, so Vi is Vs by S. Vo is all this with a negative sign here. We take partial fractions of this. We get A0CL and Vs out, 1 by S minus 1 by S minus omega CL. We take inverse Laplace transforms, we get A0CL into Vs. 1 by S is 1 minus 1 divided by S minus omega CL. The inverse Laplace transform of 1 over S minus something is e raised to something t. This is interesting. This is interesting. What is this telling us? That if we were to look at the output voltage as a function of time when a step is applied at the input, then at t equal to 0, the output will be 0 because the initial input voltage was 0. And as t increases with time, the magnitude of the output would increase exponentially with time, and because e raised to anything greater than 0 is always greater than 1, this quantity will always be negative, but will increase exponentially with time. So here is what the output would look like. This is basically an exponential. Oops, I'm sorry. This is basically an exponential. The magnitude is increasing exponentially with time. There is a sign negative. Why is the voltage going negative? So let's go back to the circuit. If this voltage becomes positive, because this is negative, the output would become negative. So assuming that Vs is positive, the output would be negative. But the output increases exponentially with time. This is what happens in positive feedback circuits. The output increases exponentially with time. But of course, in a real electronic circuit, voltages cannot keep increasing exponentially. They are ultimately limited by the nonlinear characteristics of transistors that make up that circuit. So what will happen in an actual circuit is that transistors which were usually in the active region of operation in an amplifier will go into saturation or cutoff, and overall the circuit, the output of the circuit will saturate at the power supply voltage. So for an op amp, if the negative power supply is minus 10 or minus 12 or minus 15 volts, this will eventually saturate at minus 12 volts. It kind of uh, change its behavior from exponential to saturating, and it will become constant at whatever the supply voltage is, and it will stay there. So the reason this equation, where is that equation? This equation is wrong is because this equation is derived assuming that a steady state is reached. But as we saw, a steady state is never reached in a positive feedback circuit. It is reached only when the output saturates to either plus VCC or minus VEE. Alright, so all positive, I should not say all, but wherever in a positive feedback circuit where A beta is much greater than 1, the output would simply saturate to a supply voltage. There are a small class of circuits where A beta is deliberately kept very close to 0. So let's say A beta is 0.1 here. Then this circuit would actually, it has positive feedback, but it has an extremely weak positive feedback, and it may still not cause saturation of the output. But generally speaking, one assumes that positive feedback causes saturation of the output. Okay, so this is what I wanted to kind of convey in this lecture. So this is the end of this lecture, and this is the end of our kind of digression from bipolar transistor circuits. In the next lecture, we'll go back to bipolar transistor circuits from where Professor Madhav Rao had left off before the midterms. All right.